Welcome to the lecture 20 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. In this week, we have discussed solar cell fundamentals, and in today's lecture we will solve some numerical problems based on the concepts we have discussed in this week. In last class, we have described optical loss, say front surface and back surface reflection loss, carrier recombination losses, mainly Shockley-Redall recombination and Auger recombination. And before that, in this week, we have covered solar cell fundamentals, including IV characteristics, equivalent circuits, and performance metrics. But today, we will solve numerical problems based on IV characteristics, based on calculation of performance metrics, based on carrier lifetime, etc. Let us start with a problem. Say first problem, this is a problem number 6. This is in continuation of last problems we have discussed in lecture 15. Here the figure of IV characteristics of a solar cell is given. One sun intensity solar radiation power is 100 milliwatt per centimeter square. Actually, if you follow, this power is written, but it is milliwatt per centimeter square. That means intensity is given. It is basically intensity. Maximum power point coordinate is also mentioned. First question is find out the fill factor. Second is find out the power conversion efficiency. Third is if the solar radiation is reduced due to shading such that the intensity becomes 70% of one sun intensity, determine the short circuit current density. So let us first solve the first part. Maximum power point coordinate is 0.5 volt, 125 milliampere. It indicates that the area under the curve which gives you the maximum power, which will be a rectangular area as shown here. So this gives you the maximum power area. This PM is equal to VM IM. This coordinate is 125 milliampere and this coordinate is ISC. Now you know the fill factor is equal to IM into VM, that is PM, by ISC VOC. This VM conventionally written as capital VM. So by putting the value 74.4% is coming the fill factor. Second part, the power conversion efficiency. For that you have to take the electrical power output maximum power divided by power input optical power. Since the power is given 100 milliwatt per centimeter square, you have to multiply with the area 4 centimeter square to get the total power incident into the cell. 4 centimeter square into 100 milliwatt per centimeter square cancel out. That means you don't need to change the unit. Milliampere and milliwatt, milli also cancel out. Straightforward calculation gives you 15.63% power conversion efficiency. Now the third part, this part is a bit tricky. Shading effect is considered. Generally shading due to cloud or due to other trees and other obstacle, we model the shading in terms of factor of one sun intensity. Say 0.7 of one sun, that is 70% of one sun here it is mentioned. And intensity is directly proportional to, or rather short circuit current is directly proportional to the intensity. From that you have to calculate the new short circuit current when the sun intensity is 70% of one sun. ISC, so this is 0.7 sun intensity. ISC will become 0.7 into 140 milliampere is the full sun intensity. In case ISC is 140 milliampere. So this becomes 98 milliampere. If it is ISC, so JSC, that short circuit current density, we have to find out. So we have to divide this by area. So this becomes 24.5 milliampere per centimeter square. Now the problem, second problem, there is a, say, problem 7. Consider a n plus p solar cell with n plus region doped degenerately. Degenerate semiconductor means Fermi level is aligned with the conduction band in case of n type. Here it is mentioned. And the doping of p side is less, that is 10 to the power 16. So this is an asymmetric junction. Assume that the diffusion length of hole in n plus side is Lp and diffusion length of electron in p side Ln are 70 millimeter and 50 millimeter. Consider room temperature of operation. Assume that the incident optical power produces an optical generation rate 10 to the power 20 per meter cube per second. The effective device area is 400 millimeter square and the reverse saturation current is 0.2 picoampere. Find out the short circuit current, find out the open circuit voltage. If the power delivered to the load RL is given as P is equal to V load into I load is equal to V load within bracket ISC minus I0 exponential V load by Vt minus 1. This is basically expression for the load current here, or the total current delivered to the load. So V load into current delivered to the load I load, product is this. If the maximum power is obtained for V load is equal to 0.25 volt, determine the current corresponding to the maximum power. First of all, if you draw the structure, it looks like this. This is an asymmetric junction. This is N plus, this is P. Light is incident from this side, suppose. Depletion layer width within N side is very less because this is a very highly doped, and depletion layer width within P side is greater than this. Ln value, this is the diffusion length within P region, this is Ln, and this is Lp. Carrier generated within this Ln and Lp, they separated by diffusion followed by drift, as we discussed in the basic working principle of solar cell. And the ISC, the expression of current, that is the light current, we have used IL notation in our lecture. That, if you remember the equation number 40, ISC or IL is nothing but Q times generation rate into area into Ln plus Lp plus W. W is the depletion layer width. Depletion layer width is not mentioned here, and also the data is not sufficient for calculating the depletion layer width also. As we discussed, depletion layer width is much less than the diffusion length in general structure. So you can neglect the depletion layer width. So let us first calculate the current, that is IL. We have used in our equation number 40. If you remember, IL we have used. IL is here photocurrent, not the load current. Be careful. IL, that is equal to ISC, that is Q times A into generation rate Lp plus W plus Ln. This was the formula, but this W is almost equal to negligible, say. So this becomes QAG Lp plus Ln. G is the optical generation rate. Here it is mentioned G optical. Notation is changed just. If you put the values Q, then this area is 400 millimeter square. So you convert it to meter square by multiplying it 10 to the power minus 6. 10 to the power 20 is the G, ln LP is millimeter, 70 plus 50 millimeter into 10 to the power minus 3 meter. So this gives you in ampere. After calculation, it gives 0.768 milliampere current. This is the value of ISC. For the second part, open circuit voltage. Also, you know, this is the circuit for the solar cell without any series and shunt resistances, IL and ID. So net current I is light current, the photo current, minus the diode current, ID part, which consists of reverse saturation current, that is given in the problem. Now if you like to calculate the VOC, that is open circuit voltage, from this equation you can do. Open circuit voltage means the solar cell output terminals are open. It is not connected to any load. That means in external circuit there is no current flow, and if this I is equal to 0, then IL will become I0 exponential QV by KT minus 1. Now QV by KT, actually KT by Q is again the dimension of Vt. So it can be written as V by Vt. So for open circuit condition voltage, if you replace V is equal to VOC, I should be 0. In that case, this is the relationship. If you take the logarithm and after algebraic manipulation, you can reach VOC will be Vt ln 1 plus ISC by I0. This is very important equation. This gives you IL by I0 plus 1 is equal to e to the power Q VOC by KT. Now Q VOC, KT by Q is again Vt. So e to the power VOC by Vt. And IL is nothing but ISC here. So VOC will be Vt into ln this. If you take logarithm from this expression, you can get VOC is equal to Vt ln VOC by ln IL plus IL by ISC by I0 plus 1. ISC by I0 plus 1. Using this expression, if you put the value, and Vt is nothing but 0.02585, room temperature of operation is mentioned, ln 0.768 milliampere is the current for ISC, and 0.2 picoampere, 0.2 10 to the minus 12, it will become 0.57 volt. So this is the value of open circuit voltage. And in the third part, the power delivered to the load, V load, I load, and here load resistance RL is connected. You see, this is the load resistance. What is the power? VL into IL. I is nothing but connected to the IL. Net current is flowing here. So IL minus ID, that will be is equal to I. That is I load. To remove the confusion, load current can be written as I load. Load current. So here also this is I load. V load into I load. So V load into IL is nothing but ISC minus I0 exponential Q V by KT. This V is nothing but load voltage. The voltage appearing across these two terminal, that is also appearing across the diode. So in the diode current expression Q V by KT, that V is nothing but this VL, V load, same voltage. This is V load. This explanation is given here. I load expression ultimately ISC minus I0 exponential V load by KT minus 1. If you take the derivative of P, because P is VL into I load, and if you take the derivative with respect to V load, and if you equate it to 0, because for maxima or minima this should be 0, you can get a value of V load max, it's a maximum value of V load, for which you can get the maximum power. And that expression will become 1 plus V load max by Vt exponential V load max by Vt is equal to 1 plus ISC by I0, which ultimately gives you the current I load is equal to ISC minus I0 exponential V load by Vt minus 1, and using the relation to V load max, you can get I load max is equal to ISC plus I0 V load max by V load max plus Vt, because the relationship by putting the value of Vp, dP dVL, dP dV load, this expression we have done. dP dV load, that will be 0 for a maximum power point. So that calculation you have to do, and if it is coming in this way. So if you put the values, it will coming 0.689 milliampere. The current corresponding to the maximum power. So the voltage corresponding to the maximum power is 0.25 volt, and current corresponding to the maximum power will become 0.689 milliampere. Another problem, there is a solar cell of area 1 centimeter square operating at 1 sun intensity has a short circuit current of 20 milliampere and an open circuit voltage of 0.65 volt. Assume room temperature of operation and thermal equilibrium voltage of 25.85 millivolt thermal voltage. The ideality factor of p-n junction diode eta is equal to 1. Find out the reverse saturation current. Find out the short circuit current for 0.2 sun intensity. Find out the open circuit voltage at 0.2 sun intensity. Area is given. Short circuit current is given. Open circuit voltage is given. Yeah, ideality factor eta. If you observe in expression of net current I, that is equal to ISC minus I0 into the power QV by eta KT minus 1. Actually, this eta is diode ideality factor. In the expression of diode current, this ideality factor is used. But we have considered eta 1 in our discussion. That's why we mentioned I0 e to the power QV by KT minus 1. Here also it is mentioned that eta is equal to 1. Find out the reverse saturation current. Reverse saturation current is I0 here. ISC is given. VOC also given. IL also we can write, I light, we have used in our equation, that is equation number 41. IL is light current is equal to IPH is nothing but ISC. Be careful. And open circuit voltage from logarithmic this eta Vt ln 1 plus ISC by IC. If you use this expression, eta will be appearing here. But eta is 1, so you can neglect this eta value 1. Vt is thermal voltage. ISC short circuit current. So find out the reverse saturation current. So first part you have to do this eta 1. 0.65 volt is VOC is equal to Vt ln 1 plus ISC by I0. ISC given, I0 can be calculated from this formula. ISC is 20 milliampere. I hope it is 20 milliampere. Yeah. So then you can get the value of I0. This is 2.40 into 10 to the power minus 13 ampere or 0.24 picoampere. This value is coming. The second part is short circuit current for 0.2 sun intensity. Similar problem we have discussed earlier. So short circuit current directly proportional to the sun intensity. So ISC when the full sun it was at 20 milliampere, so it will be simply 0.2 into 20 milliampere, so 4 milliampere. And as the ISC reduced to 4 milliampere, so open circuit voltage correspondingly can be calculated from the relationship VOC at 0.2 sun. Again the eta Vt ln this, but eta is equal to 1 here. You can get 0.61 volt. Another problem. This will be say problem 9 here. Consider a P plus N solar cell with the P plus region doped degenerately. Fermi level in P side is coincident with the valence band maxima. The doping of N side is 10 to the power 17. Assume that the electron mobility and lifetime in the P region is 800 centimeter square per volt per second and 1 microsecond respectively. And the whole mobility and lifetime in N region are 200 centimeter square per volt per second and 10 microsecond respectively. Consider room temperature of operation. Find out the values of LP, diffusion length of hole in N side, the values of Ln, diffusion length of electron in P side. Find out the short circuit current ISC if the incident optical power produces an optical generation rate of 10 to the power 25 per meter cube per second. Effective area is given. So it is easy, you know. If the reverse saturation current is given, find out the open circuit voltage. Similar problem, but here it is P plus N junction. You have P plus N junction. Depletion layer width within the P region will be very less, slightly within N region, and the diffusion length within N region, that is LP, minority carrier diffusion length within P region, this is Ln. Find out LP and Ln. You have to find out LP and Ln. So formula for LP is equal to root over dp tau p. dp into tau p is given lifetime, but dp is not given. How can you get the dp? dp is kt by q into mu. That is the Einstein relationship. Mu is given, and if you calculate the value of mu, if you put the value of mu, so dp will be obtained, and by putting this dp you can calculate the lp. So this dp 5.17 centimeter square per second. So lp is equal to dp tau p 5.17 into 10 microsecond in case of hole in N side. Whole mobility and lifetime is 10 microsecond. it ultimately calculation gives you 71.9 micron. Whereas ln would have a dn tau n, but dn is again d by kt by q is into mu n, because d by mu is equal to kt by q. So this value is 20.68 coming, and putting this value ln will become 4.55 or 45.5 4.55 into 10 to the power minus 3 centimeter. That means 10 to the power minus 3 centimeter, 10 to the power minus 5 meter. The 45.5 into 10 to the power minus 6 meter, that is 45.5 micrometer. You see, LP is more than ln here for this particular problem. First 1 and 2 part is completed. Find out the short circuit current IC if the incident optical power produces generation rate 10 to the power 25 per meter cube per second. In same thing, short circuit current IC is equal to Q times area into G into ln plus LP plus W. W you can neglect. Yes, this is given. Putting this value, ISC will become 18.78 milliampere. And the fourth part, VOC, that the formula here 1 plus ISC by I0, but 1 plus term is neglected. VOC is equal to VT ln 1 plus ISC by I0. If you see the ratio of ISC by I0, this much greater than 1. So this can be approximately written as VOC is equal to VT ln ISC by I0. Or you can use also 1. No issue, the calculation. But here calculation is done without considering 1 value. It gives you 0.646 volt. Be careful over the unit. VT is 0.02585 volt. I0 is 2.6 10 to the power minus 13. ISC is given. Here calculation is shown. If 1 is considered, value would be 671.646.671. It would be coming. I can write here ISC by I0 much greater than 1. So this one neglected, can be neglected. Another problem is find out the minority electron lifetime in a p-type semiconductor. Minority electron lifetime in a p-type semiconductor. Of course, minority electron lifetime in p-type, because minority carrier is n in p. If the capture cross section is 10 to the power minus 16 centimeter square, thermal velocity of electron is 10 to the power 5 meter per second, and density of trap states Nt is 10 to the power 13 per centimeter cube. It's very straightforward formula. Tau n, inverse of sigma Vtn Nt. Sigma is capture cross section, Vtn is the thermal velocity, Nt is the density of trap states. 1 by this 10 to the power minus 16 centimeter square, 10 to the power minus 4 into 10 to the power minus 4, because per meter square it is considered. Per centimeter square is converted to the meter square, into 10 to the power 5 meter per second, and 10 to the power 13 per centimeter cube, it is converted to per meter cube, so 10 to the power 19. It gives you 10 to the power minus 4 second or 100 microsecond. Yes. Or you can say 0.1 millisecond. 100 microsecond. This is the carrier lifetime. You see the value, order of value, this is 100 microsecond. So today we have solved 4 problems, numerical problems based on IV characteristics, performance metrics like short circuit current, open circuit voltage, power conversion efficiency. Also we have discussed or we have solved a problem related to the maximum power delivered to the load. And you just be careful about the notations. Load current, photocurrent, short circuit current, they are denoted as different notations. Also we have solved a problem on carrier lifetime and we have seen the value is in the order of 100 microsecond. But if we would use capture cross section more, lifetime would be less. That is, more chance of recombination would be coming. These are the references for the problems. Thank you.